Well, welcome everyone. Thank you for coming. My name is Paul Cotting. I'm on the product management team at EMR.
Hey, I'm Vinod, and I'm a PMC lead on the Apache Hudi project.
Awesome. And so today we're really here to help you better understand the specific types of use cases that Apache Hudi can help you solve. We're going to walk through how Hudi works and how it's been used in production at Uber for over 4 years to help them solve some of their data management challenges. And we'll start by outlining some of the traditional use cases that are hard to solve without a solution like Hudi. We'll talk about the kind of motivating use case at Uber and what led them to create the project. And then we'll talk about the architecture and exactly how does Hudi work, how do you actually manage data using Hudi. And so let's start by going through some of the existing use cases that are just a challenge to solve today without a framework like Apache Hudi. So for those of you in the audience that may not be familiar with the General Data Protection Regulation, or GDPR, or now the California Consumer Privacy Act, CCPA, these are data privacy regulations that have started to go into effect late last year and have driven a lot of new use cases, specifically around making sure that if you're a company that's processing user data or user profile information, you give your users the ability to, on an on-demand basis, remove that data, effectively give them the right to be forgotten. And these are use cases that can be just really challenging to solve, because first you have to figure out where are the individual records stored, which individual files, which individual partitions contain the records that you want to be able to remove. And there's no global index that's just automatically created on your data unless you've actually engineered a solution for that. So you have to first figure out where all these individual records that you need to delete located. And then you have to go about doing the deletion operation itself. And for many of our customers that have approached this specific use case, they struggle because they have to not only read the entire data set, remove those specific records, but they have to rewrite it, which can be very I/O intensive and can lead to a lot of just unnecessary write operations just to remove a very small number of records from their data set. The next use case for many, it might have been one of the first use cases that you built a solution around, and this is getting high-value data from RDBMSs into your data lake. And it can be really simple to ingest, do like an initial bulk ingest of this data, but the challenge is really around how do you keep that data fresh? How do you keep the changes that are occurring in those databases flowing into your data lake? It's very easy to get access to the different change logs, so you can see what data is being inserted, updated, or deleted. The challenge is really how do you apply those changes to your data sets that are stored in S3. Bulk loads are something that don't scale well. You don't want to be ingesting the entire database every single night. What you really want to be able to do is just say, show me what's changed. And so you want to be able to update that or upsert that information. And it's a challenging use case to solve without something like Apache Hudi. And the last is, in order to be able to make business decisions based on your data, you have to trust that data. You want to make sure that the data is quality. And if you run into a situation in which an upstream system gives you some bad data, you have the ability to actually get out of that scenario. You want to be able to maybe restore it to a save point or roll back individual commits. You want to be able to have that data to get out of a tough situation if you're handed bad data. The next is around streaming use cases. These streaming use cases are becoming much more popular and more heavily adopted. And these use cases call for a new set of requirements to quickly ingest high volumes of event data and store it in an efficient format that really matches how that data needs to be used. So how these data sets are actually used is important because it really affects how they should be stored. Some data sets are very write-heavy, optimizing for high-speed ingestion over read performance, while others are read-heavy, optimizing for performant reads while making a trade-off on write performance. And it's important to have that option to choose, as each use case is really different. And the one thing that I know many people suffer from is dealing with the small file problem on either S3 or HDFS. You really want to be able to have a system that helps you manage those individual file sizes, make sure that you have, instead of a lot of really small files, a smaller number of large files, so that list operations as well as query planning can be done in a performant manner. So next, what I wanted to do is kind of, with those challenges in mind, talk through what are some of the use cases that Uber dealt with and what led them to the creation of Hudi.
The clicker?
Yes.
All right. Yeah, so all of these, you can hear me, right? All right. So all of the three challenges that Paul just mentioned, enforcing data privacy regulations or kind of streaming ingest or applying database change logs, they all manifested in kind of like a very central core data set at Uber, the Uber trips data set. So what happens is, I was at Uber for a good amount of time working through various different generations of Uber's data infrastructure. And what happens is every few minutes we get a lot of new trips and as well as a lot of updates to existing trips that span across multiple past days, months, or even years in some cases. So the use cases that actually generate these kinds of updates to older partitions even are things like you may have taken an Uber a month ago and you pull up your app and then you rate a trip which happened a month ago, or you provided a credit card which didn't work and then you had to retry the payment with another credit card, some other mechanism, or you simply didn't like the Uber trip, you complained, and then the fare got adjusted. So all these updates keep kind of coming in, and since this data set is a very critical data set at Uber, everyone wants this updates and deletes to be kind of applied as quickly as possible so that more downstream tables and more processing can actually begin happening, right? And then doing this naively costs a lot of I/O because the spread of the partitions is too high. You have to rewrite a ton of data. And then on top of this, all of this needs to be updated with kind of uniqueness constraints. We cannot have duplicate trips, say, because we'll run some reporting to look at how much money we made in a city, yada, yada, right? And then we also need this to be transactional. The dirty data cannot get in. You can't suddenly read corrupt trips, things like that. So, and it doesn't stop there, right? I mean, because usually once you ingest, you don't stop there. You build more derived tables on top of it. For example, at Uber, there are tens of trips tables which are deriving their own kind of views of the raw trips table. For example, there was a table, say, that all it does is say the raw trips table has fares in the local currency, and then you wrote a simple ETL job to standardize all the currency to USD. Right now, going back to the use case, if the fare got updated, you now need to update this ETL derived table as well. So this just goes across the entire ecosystem. And then, so this basically needed some more holistic thinking on how to manage the data movement and how we propagate data across these stages. So we started with a fairly typical architecture, which I'm sure it's prevalent even now. So to deal with updates, you spin up a key value store. We use Apache HBase. So you take all these updated tables, update HBase. So HBase has the latest snapshot of your upstream database. And then every few hours, a Spark job runs. It bulk converts all of this HBase data into a bunch of raw tables. And then every few hours, more bulk batch jobs run, and then they fully convert all these raw tables into these kind of derived ETL views that we want. So there are a bunch of problems here, right? Obviously, this is too slow. You get the trips data in the derived trips after 12 to 24 hours. This was very unacceptable, at least at Uber, where the business was very real time. Trips happen in real time, things change, and we need to respond. And the ETLs, they lack intelligence for recomputing. Even though, say, only 500 GB changes, they full table scan all these raw tables every time. And it just costs wastes a lot of resources. And then whenever we try to do things incrementally, we keep running into small file problems. So you can ingest very quickly, but then someone has to clean up all the small files you generate, right? And then a whole bunch of issues around you can ingest a bad batch of data. How do you prevent the queries from seeing them? There are no transactional fences or guarantees on when you're managing files manually on HDFS or S3 or any of the cloud stores. And how do you avoid duplicates? How do you enforce that there are no duplicates getting into your tables, right? So we started thinking, the core idea, we distilled it down to, hey, we can't do these bulk batch jobs. They're too unwieldy. We have to really get down to doing things more incrementally. And then this is the kind of the evolution of where we started from for the last 4 years. We first published a bunch of these principles on an article just to get more feedback from the industry as a whole. Also to kind of sanity check that we're not talking about imaginary problems. And then we created the project at Uber, powering all critical tables. And we open sourced the Hudi project in 2017. And we also, at that point, Uber moved most of its data into Hudi, having like a massive 100 petabyte data lake now powered using Hudi. And 2018, we started picking up more open source adapters, and most of these people were using S3, non-HDFS storage. And then so we generalized this for also cloud storage. And then earlier this year, we entered into the Apache incubation program. And because ultimately this data is kind of like source of truth data in every organization, and we wanted to kind of evolve this project in a kind of an open, vendor-neutral way, written in purely open source file formats, and we are now currently working towards graduation. So hopefully we've advanced this state of the art that we discussed before, and here is what you can do now with Hudi. For the same use case, you don't need HBase anymore. You can directly take your updated, your change logs and apply them directly on these raw tables using a Hudi upsert operation. And then additionally, Hudi also gives you the change stream of what exactly changed in a data set from a given point in time. So you can actually use that to, going back to our example, you can actually use that to compute your fare update. Right? It's going to hand you the new fare raw trip column record, and then based on that, you can apply your currency conversion and then upsert it again into your derived table. So this whole thing becomes more incremental. We move away from big batches. Imagine a big batch failing after running for 7 hours. It's wasted all this CPU that in the cluster that you cannot really reclaim. So we are moving more and more towards incremental and doing things in a more streaming fashion. We completely rethought this as a database problem, also considering the fact that this has to now scale for 10 to 100x more data than your typical, say, OLTP database, optimized for analytical workloads, and we also provide a lot of tunable trade-offs. So if you really want data freshness over, say, columnar query performance, or do you want columnar query performance, we expose different views of the data as you will see moving forward. So with that kind of context, let's dive into Hudi. So what is Apache Hudi, and why should you care? Hopefully, I can give you a few good reasons. So with Hudi, as you will introduce, you can do near real-time data ingestion. It comes with like a kind of a self-managed ingestion tool to do that. You can quickly ingest data from your databases or Kafka or wherever you have your data onto S3. And if you have batch jobs which are scanning a lot of data or rewriting a lot of data, you can potentially use Hudi to kind of incrementalize them and kind of like make them faster as well as save on cluster resources. And if you really like stream processing, the style of writing jobs, Hudi actually gives you primitives finally to write stream processing style jobs on top of batch data. Typically, you write stream processing on Kafka data, and then you write batch jobs on S3 data. This actually gives you the ability to do more streaming style incremental processing jobs on batch data itself. And finally, by bridging this kind of data latency gap, you can move more and more use cases into the same S3 analytical storage. So it kind of also serves to unify a lot of these use cases for you. Like the near real-time use cases can just stay in S3 now, as opposed to taking people running separate data marts for those kind of use cases. And finally, as we mentioned before, it lets you apply deletes to enforce your privacy regulations. Overall, it gives you a lot of building blocks, and it's a good platform to build data lakes on. So, cutting to the technical details, it supports upserts. So you can, it's either an update or insert with fast and pluggable indexing. So Hudi tries to actually build uses Bloom filters, range information to build kind of record level indexes to quickly update data. You can atomically publish data to a Hudi dataset and you can also, with the ability to also roll it back, and also kind of denote save points, which are kind of snapshots that Hudi will preserve. This way, if anything bad happens, you can come back to that point in time and then resume. And then it provides snapshot isolation between writers and queries. What this means is when you're writing data into a Hudi data set, you can query. The queries, writers and queries don't block each other. And then the queries always query a consistent snapshot of the data, so you can reproduce the query if you want to go back in time. And it automatically manages file sizes and layouts to you. So if you use Hudi, what you will see during writing is that it is doing a whole bunch of other things. And while it may be very tempting to look at that as overhead, what it's actually trying to do is it's trying to do heuristics to size your files so that you always write, say, 128 MB or 256 MB sized files. This way, your queries will later thank you because they are always running on good sized files, as opposed to kind of like quickly writing a whole bunch of small files and then letting the query actually query them, and then later compacting. So we make a conscious attempt by incurring more, kind of spending more time on the writer side to size the files properly. And again, like these things we had to do out of the box because we were running Hudi for 3,000, 4,000 tables at Uber. So this kind of had to be done at a platform level. And again, so it also has the ability to kind of asynchronously compact your row-based and columnar data sets. And it internally tracks all the actions that you perform on a data set in a timeline. And this can be used to build a lot of other cool features as well.
Cool, thanks, Vinod. And so what I want to do now is just kind of cover what's the architecture of Hudi at a high level, and then we'll drill into all the details, and you can see exactly how Hudi manages your data on S3. So to start with it, at the heart of Hudi is the dataset. And the dataset can be written in a number of different ways. One of those options to write data into a Hudi dataset is to use Delta Streamer. Delta Streamer is a CLI tool that allows you to watch specific locations within S3 for new files. It can read those files and stream those events into your dataset. It can also attach to a Kafka topic and look and listen for events and stream those events into your dataset. You can also use the Spark data source. So if you have existing Spark jobs that you want to be able to use to create new data sets or insert, update, delete data, there's a Spark data source available for that. Once you have data in your data set, then it comes to actually reading it. As Vinod had mentioned, there's different views that Hudi gives you on top of a data set. Incremental is a view that allows you to get a stream of changes that have occurred on that specific table, either since the last write or from a specific point in time. So it allows you to answer questions like, show me all the rows that changed as of, since yesterday, for example. And that will give you just those rows that have been changed since a specific point in time. There's also a read optimized view that gives you a columnar read performant view of that data. It will give you the kind of a list, effectively access to the entire data set at the point of its last compaction. And then there's the real-time view. And this real-time view gives you access to the entire Hudi data set, including near real-time access to changes that have been made to that specific data set. So now we'll take a closer look at some of the moving pieces within the data set itself. So as I mentioned, you can use Spark to write to your Hudi data set, and there's really three big moving pieces within the data set itself. There's the index that allows you to map individual records to the specific data files that those records are contained in, as well as the timeline metadata that shows you all the different actions that have been performed on that specific Hudi data set. There's no persistent daemons that are part of Hudi. All this information is stored with the data on S3. When it comes to the specific applications you can use to query those data sets, we support Hive, Presto, as well as using Spark SQL to query that data. So next, what we want to cover in more detail are some choices that you make when you create a Hudi data set. There's really two different storage types that you can choose from when you create a data set. The first is copy on write. And this is good for read-heavy use cases in which you have maybe a smaller number of writes and you really want to bias toward always having a highly performant read copy of that data. And then there's merge on read, which is more for write-heavy use cases in which you want to have near real-time access to data that's being streamed into these data sets. So now what we're going to do is Vinod's kind of going to walk you through each of the different storage types and how data is manifested in these views.
All right. Right. So now let's actually take the copy and storage type and actually understand how internally it manages the files using an illustrative example. So we start with an empty data set. Let's say we insert kind of 5 records, A, B, C, D, and E. And they get distributed to 3 files that internally, like I mentioned, Hudi chooses how many files to choose based on how much data you're inserting. And then all of these files, every write operation inside Hudi is assigned like it's called a commit, and then it assigned like a commit time, which is kind of analogous to SCNs or transaction IDs in relational databases. And in this case, there's file 0 with 2 records, file 1 with 2 records, and then file 2 with 3, right? So the read optimized view will simply read the latest snapshot of the database, the data set. So you're going to read A, B, C, D, E if you do a select star on this whole entire data set. The incremental, again, what you wrote in the last commit is essentially these 5 records. So both of them return the same value at this point. Now let's introduce updates. Let's say you update D to D prime and A to A prime. So Hudi will basically internally figure out which files these D and A are part of, and then selectively version these files at a commit time 1, generates another commit. So you have file 0 prime now containing A prime, and then file 1 prime is the first version of file 1 containing D prime. And then at this point, if you issue a read optimized query, now you are again querying the latest snapshot as of commit time 1, which will give you A prime B, C, D prime, and then the content from file 2, in the latest version of file 2 basically, which gives you E, right? So the incremental view is going to basically give you the records that changed after commit 0, which is basically everything that you wrote in commit time 1, so you get A prime and D prime. Let's say we do upserts, like a mix of updates and inserts, so where you are updating E to E prime, you update A again to A double prime, and then you insert one more record. So like I mentioned, Hudi is going to figure out that, okay, file 2 is the smallest file, so that's where I should pack the new insert. So it's going to generate version file 2 by adding both the update E prime and then add the new F record in that as well. File 0 gets versioned again as file 0 double prime, and then now if you query read optimized view as of commit time 2, you're going to get A double prime, B, C, D prime, E prime, and F. Once again, incremental view will always only give you the changes from commit time 1 if that's what you ask, right? So you're getting whatever you wrote in, you'll always get out of incremental view. So when do you use this? If your current job is rewriting entire tables or entire partitions to deal with updates, you can just use copy and write. And since it selectively only rewrites at the file level, you'll probably see an order of magnitude improvement already. But in order to do so, make sure your workload is fairly well understood, because if you have sudden bursts in the workload, you can imagine that you'll suddenly be versioning a lot of files, and then you can kind of degenerate towards what you're doing today, right? And if you're using Parquet files today for your tables and you want to keep it simple, have a model, essentially a batch job which just does a faster job of updating and managing data, copy and write is the simplest choice that you can pick out of the box, right? So now let's go on to merge and read. This is a much more advanced and a kind of flexible storage type which has more moving parts. You can do compaction synchronously, asynchronously. It is far more advanced. And let's see how that behaves. Let's take the same example. Let's insert the same 5 records. There's no difference till this point because it just creates. It sees that there is no data, so it just creates the Parquet files. You get file 0, file 1, file 2 as before. There's an additional view now called the real-time view, which I'll explain in a bit. But for now, as before, all 3 views see the same data. Now let's introduce the update. D to D prime, A to A prime. What happens now is instead of a commit, we do a special kind of commit called a delta commit. So instead of entirely rewriting these files, what we do is we use the indexing. We figure out that D and A are touching file 0, file 1. and we create a log corresponding to each file, and we simply store the update that you wrote, the updated values in the log. Now, when you query this data set using the real-time view, what happens is we merge the log with its corresponding file on the fly during query side, and then give you the latest value as of delta commit time 1. So in this case, you get A prime B from the file. You get A prime from the log, B from the file. You get C and D prime from the log. And then file 2 does not have a log, so you get what's in the file. And then incremental, it behaves the same way. You just get what you wrote in the delta commit. The read optimized view, if you know, always returns only the values in the base files, not the logs. It never reads the logs. So this way, the base files are typically columnar Parquet files. So you always can run, if you're running a large machine learning training job and you don't want to incur this merge cost and you can tolerate data staleness, you can, for MOR, you can use the read optimized view to simply keep your queries on columnar data. So that's the kind of intended purpose for that. So let's move along. Let's now do the upserts that we did before, E to E prime, A to A double prime, and we insert F. So we add an additional entry to log 0. It has now A double prime as well. And then we create a new log entry, log for file 2, with both E prime and F. The real-time view, again, is going to merge everything and going to give you sort of A double prime, B, C, D prime, E prime, F. Incremental, again, gives you what you just wrote in, which is A double prime, E prime, F. And then read optimized view still returns what's in the files, not touching anything that you wrote in the log. So finally, you can configure the compactor to run based on different criteria. When the compaction runs, it merges the logs and the files, and you get the latest sort of view, which is similar to what we saw in the previous query. But now you can see the read optimized view and the real-time view finally kind of catch up. So this is what it happens, and doing something like this manually by hand, like managing files, is like very cumbersome. So Hudi kind of under the hood manages all this for you under a nice API. And when to use this, you can obviously, since we're not recreating the file every time, this is much faster than sort of copy and write. You simply log, and you can get like you can write data as fast as you can. And the main thing here is the workload can have sudden bursts. Like for example, when you're doing these deletes, they usually have much different pattern from your normal normal ingest traffic. Suddenly you want to delete data going back a year or something like that. If you use copy and write or any other technology which is rewriting files, suddenly your job is going to get clogged because it's doing a lot more work. So merge and read is very nice because like you can configure a compaction policy which always only compacts the recent data more aggressively and things like that. So it can absorb a lot of variation in the workload, and this is very, very helpful for when you're dealing with large-scale data with the GDPR and those kinds of privacy regulations. Right.
Cool. So now let's take a closer look at just what are the different options you have to write data to a Hudi dataset, and we'll talk about some situations in which you might want to use one or the other. So we had briefly mentioned Delta Streamer before. So Delta Streamer allows you to watch a specific S3 location for Avro or JSON files, and as additional files get placed in that specific directory, Delta Streamer will pick those up, parse them, and then update your Hudi dataset with the data that just landed in S3. It's very similar on the Kafka side. It can attach to a Kafka topic and listen for events on that Kafka topic, either in Avro or JSON format, and stream those specific changes into your Hudi dataset. There's also a utility called the Hive Incremental Pull that allows you to connect to an existing Hive installation, issue a query, and then the results set from that query can be used to populate your Hudi dataset as well. So when would you want to use one over the other? In this case, using Delta Streamer is really helpful if you want a kind of completely self-managed, codeless way of ingesting data. It will automatically handle data compactions. It'll also automatically handle checkpointing. So as you're looking at maybe ingesting data from S3, as Delta Streamer is running and ingesting new files, it's constantly checkpointing where it last left off. So if you have to effectively kind of turn the Delta Streamer off, then put it back on, it knows exactly where it left off. Additionally, like I said, if you want kind of a codeless solution to ingest data from those two sources, Delta Streamer is a great solution for that. And lastly, it also gives you the ability to add transforms in the process. So out of the box, it has a SQL-based transformation capability, so you can specify a specific SQL statement. It could be column projection or filtering or casting data or whatever, what have you. And that will be applied to each of the events as they come through Delta Streamer. It also has a pluggable mechanism for additional transformations. So if you have more complex or advanced transformations you want to apply to that data, you can plug those into Delta Streamer. The next is using, in this case, just say the Spark Data Source API. So this is really helpful if you have existing Spark-based ETL, and instead of writing Parquet files out directly, you can then just with a few different format and option statements, write that data as a Hudi data set. So this is really helpful if you have, like I said, existing ETL pipelines that are maybe sourcing data from multiple data sources. You want to combine and create derived tables. You can use Spark Data Source for that. It's also helpful if you want to be able to read and write to both Hudi and non-Hudi managed data sets. And lastly, you can use it with Spark Structured Streaming. So as events are flowing through, you can then use this data source to populate and update your data set. Cool. So next we want to talk about, once you have data in your data set, what are some details about querying that data set? So here on the screen, we have a table that shows the different engines that are supported to query data sets and the specific views that are also supported. So one of the things that a lot of customers ask is, okay, you have these different views, but how exactly do you configure Spark or configure Hive to take advantage of those views? And we wanted to walk you through some details about how each of them can be used. One of the great things about Hudi is when you create a Hudi data set, you have the ability to say, hey, I want to also create metadata in the Hive Metastore or the AWS Glue Data Catalog. So if I create a data set, it'll create corresponding tables within that Metastore, so you can more easily use it with these different engines. So now what we'll do is walk through each of the different engines and show you some examples of how to use the views with each engine.
All right. So for Spark, Spark supports all these three views, and querying both the read, optimized, and real-time views are as simple as writing Spark SQL statements, just like any other Hive table. For incremental view that we saw before, what you do is you use a Spark Data Source API. If you're familiar with this, you pass in a view type saying, I want to query the incremental view, and you also provide the begin commit time from which you want to stream changes for the data set out from. Hive, very similar. You just write queries against both these views like any other table. Incremental needs more inputs. You have to tell the Hudi Hive input format that, hey, this particular query is running in incremental mode. Here is the start timestamp, and I want to get 3 commits out of that if you want to say that you can do so. And this query, for example, is going to fetch all the sales that were entered for the state of Nevada after that given commit time. So Presto right now only supports the read optimized view. We are actively working with the Presto community to get both the real-time view supported. There are large changes in Presto that's needed for that, but we are hopeful that we can land that in the next couple releases. All right, so now let's actually take a more deeper tour. We'll try to use the data source API more and see how we can interact with the Hudi data sets. You're going to see a lot of code. If you're familiar with Spark, Scala, you can follow along. But even if you're not, I think we're keeping it like fairly high level, so you should be able to follow along very quickly. So here we'll be using the Spark shell, which provides an interactive way for us to sort of issue Spark or Scala code and interact with Hudi datasets. And first, let's just import some code. And the data format that we'll be using in these examples, models like a changelog for an Uber trip. So this is like the latest version of a Uber trip as we obtain from an upstream store. So each trip has a unique UUID. It has a timestamp for when this change was made. And also it has a partition which kind of contains a folder structure for a continent, country, city in which this trip happened. And so first, let's just look at how to simply insert data. Let's say you don't even have any updates, but all you want to do is simply insert some data transactionally into Hudi. And then, so the first time you do that, all of these indexes and so they don't exist. So the first commit is going to create the first versions of all of these, set up the kind of the folder structure for your data set, and then after it's done, it's also going to register the tables create the tables on Hive Metastore. But let's move on. So let's generate like 10 inserts, which gives you essentially JSON records of that format, and all you need to do is convert that to a data frame somehow, and then you use the data frame writer with a few key inputs. So you need to tell it what is the UUID in your input. So Hudi works with a key always. It kind of needs a primary key in your data set. You specify it how to partition your data set using the partition path field, and you also specify a pre-combine field key. So this may seem a little bit like a lot of options here, but these are all needed for good purpose. So the pre-combine key helps us sort of deduplicate within a given batch. So for example, if I have change logs, multiple change logs generated within a given commit, and you want to only say apply the latest change log, so you have to pick the latest value, right? So it helps us kind of rank these deduplicate kind of records within that batch. So here what we are doing is we are picking the record with the, if any record has the same UUID, we are picking the one which has the highest timestamp. And then you issue an operation. The operation can be insert, upsert, and soon delete will also be a first level option. And then you just give it a path to save the data set to. And then what happens, what you'll immediately see is after this commit is succeeded, there's a .hudi folder under your data set. And then it internally has a bunch of these files, including a file for the commit that you just made. And let's make it more interesting. Let's say we want to deduplicate this data as you insert it. It's a common case for event streams. If you're mirroring Kafka data through multiple data centers, you may have duplicates, and then people normally want to deduplicate this data set. So if it's a duplicate, you want to skip it, else you want to insert it. So it's as simple as setting an option to true inside Hudi, where if you do this, then Hudi is basically before it inserts, it checks against the index, make sure these records don't exist, and then only insert the records that are unique. And as you can see, the counts for the distinct and the count are the same. So essentially, it enforces no duplicates in your data set. So we talked a lot about incremental streams, right? So in this example, what we're trying to do is, and even in our example, we talked about how to get the changes that were made in a given commit. So in this example, what we are trying to do is we are trying to fetch the records that got changed in the second commit only. Basically, we just did 2 commits now, right? First one without duplication, and the second one after duplication. If you want to get the changes that we made in the second commit, what you do is you create use the data source API, but you specify the begin instant time as the first commit. So it's going to filter every record that got written after the after the first commit. And Hudi tracks per record metadata, so it will accurately only give you the records that got changed after a point in time. And let's make it even more challenging. So by trying to update some data, right? So what we want to do here is, if the record already exists, we want to issue an update, and if it doesn't exist, we want to just insert the data, right? So let's begin by simply generating just 10 inserts and creating like a new data set. Everything else remains the same. All you need to do now is change your operation from bulk insert to upsert, and then you can even issue inserts. It just works. You don't have to have updates to issue the upsert operation. Now our data set has 10 new records. Now let's generate 5 updates. Essentially pick 5 of those and generate an update for them. And then again, nothing really changes. You just issue this again as an upsert operation. And what you'd see now is you're distinct. You still only have 10 records in your data set. And then if you group all these records by the commit time, so this is the per record metadata that shows when a particular record was changed. You can see that they're evenly split across the two commits that you made now. So you inserted 10 and you updated 5 of them. So you get 5 for both the commits. Finally, deletes. So here, there can be 2 kinds of deletes, like soft deletes, where you want to keep the record key retained for matching to other stores, or you want to just get rid of the entire key as well as the record, right? So soft deletes can be simply implemented using just an update. It's just an update with null for every other field, right? So, but let's now simply look at how we can implement hard deletes using some Hudi. So hard deletes, you still use the upsert operation, and then in the next release we are actually introducing a top-level delete operation to do this much more easily. But in the current release, what you do is you use a upsert operation, but you specify a special kind of payload class. So this payload class, since we haven't talked about this before, is a mechanism in Hudi that specifies how an incoming record needs to be merged with the with the record that's already on disk. Like for example, you may want to simply overwrite the existing value with the incoming record, or if you're in case of say another thing that my team built at Uber was a network monitoring dashboard, where what we did was we took some metrics and we kept aggregating them with the current value on disk. So for example, you are counting number of trips, and then you have already existing counts on storage, and you can actually write a payload class which simply adds the new incoming values to the old value, just like how you would do it in stream processing jobs. So in this case, cutting back to deletes, you specify a special empty record payload, which essentially always throws away the value on disk and returns a null empty value. So this effectively skips the record, and it writes delete markers, and eventually when compaction runs, this data will go away from the data set. And as you can see, we kind of deleted 4 records and from this whole data set, and if you delete it, then you will have remaining back. Okay, rollbacks. So sometimes bad things happen, and then you want the ability to roll things back, right? And Hudi provides tooling that helps you do this. So Hudi actually has a extensive CLI, which helps you connect to a data set and kind of manage it. You can look at comp actions that are scheduled, you can unschedule, you can view a whole bunch of things. But for now, let's just focus on how you can work with commits. So you can just say connect to a data set and say Hudi commit show. It gives you sort of all the commits that have happened to the data set with some basic stats about how many files were touched. You can see what's going on. All of these are also metrics. We have metrics that are emitted to Graphite or wherever that you wanted to also visualize some of these. And then by rolling back is as simple as saying commit rollback this commit. So just wanted to give you guys a point on, hey, there's a CLI which helps you manage the data set.
Thanks, Vinod. So I think what we want to do is kind of wrap up and to summarize. You can use Hudi today using EMR 528. So the latest edition of EMR 528 includes Hudi. It's compatible with Spark, Hive, and Presto. So when you're launching your EMR cluster, if you choose Hive or Spark or Presto, Hudi libraries will be automatically in your cluster. You don't have to do anything to additional configuration or additional installation. Hudi is just there. And we support both the Hive Metastore as well as the AWS Glue Data Catalog for storing metadata. So I want to go through just kind of quickly how are some of the different use cases that Hudi can help you with. Number one is data privacy law compliance. So as we had discussed in the beginning, GDPR, CCPA, you want to be able to enable you to delete your user data quickly. With the index that Hudi provides, you can quickly find the individual rows and only rewrite the specific files that you need to rewrite to delete sensitive information you want to remove. The other thing is consuming and applying CDC logs. So once you've gotten those events from your database, Hudi helps you quickly apply those by just upserting data into your data set. The next is reinstating late arriving data. So as data comes from upstream systems, it's very easy to just hand that data to Hudi. It'll deal with the low-level file management of updating the right partitions, updating the right files on S3, and managing that for you. And then lastly, being able to track the individual changes you make to your specific data set and rolling back those commits as we saw using the CLI or using save points to revert your data set back to a specific point in time. Hudi gives you the ability to do that. And lastly, it just gets you out of the whole game of having to manage each individual file in S3. Hudi provides that layer. You just tell it insert, update, delete. This is what you want to do with your individual records, and Hudi will take care of all the details underneath the covers. So what I wanted to do now is just kind of have a note talk about the open source community, and if you want to get involved, what that process looks like.
So we are, as I mentioned, we are part of the Apache sort of Foundation incubator process right now. And then we have, we are a fast-growing community. The project is evolving very quickly. There's a lot of technical challenges ahead. And we have some very diverse PMC members. And we are, we welcome contributions. And if you want to get involved, here are some resources for you to get started. All of our kind of product-facing documentation sits in the Apache Hudi.apache site. Here is where our code lives in GitHub. Our Twitter handle. You can subscribe to our mailing list where most of the discussions happen. And then we also have a FAQ if you have more follow-on questions on a lot of different aspects of Hudi. It kind of accurately summarizes where the project is, and in some cases gives you guidance about where the project is also headed. And with that,
yeah. And so lastly, if you're using Hadoop, using Hive, using Spark, using Presto on-premise today, and you're looking to migrate to EMR, we have a lot of really great resources. We've recently published a detailed migration guide that walks you through a lot of the decisions that you might have to make, the process you might have to follow when moving from an existing Hadoop distribution to EMR. And to personalize that, we also have a free on-site 2-day workshop where we will come in, help you identify what that future state architecture looks like with EMR, and help you chart out that migration path. So if you want any more details on migrating to EMR, you can just visit our EMR migration website or feel free to email us to get that set up. And lastly, you've come to reInvent to learn, and that learning doesn't have to stop when you leave. We have a lot of great AWS training and certification resources. Feel free to visit our website and look for the big data specialty. Thank you. Cool. So with that said, thank you very much. It's been great talking to you.